Welcome back for another day of fun. I don't know how you guys actually find this, but I find it intriguing at the very least.
Okay, so
it's challenging but fun. Go ahead.
Your video wasn't posted last night, so I wasn't able to see this slide. So could you leave it on the slide for a second? So
Sure. Which part?
Okay, thank you.
The top part or?
The middle. No, not the middle. Like the middle of that top part.
Okay, so you want?
Yes.
Yes, it's actually funny. I uploaded the other two and forgot the third one. Well, I mean, it's funny. It's disappointing. But. Okay, so what we've established here, and I want to make sure we're keeping some continuity of thought. So we started with that simple harmonic oscillator Schrodinger equation, and then we recognize, of course, that kinetic energy is p squared over 2m, so we could write the Hamiltonian in terms of the momentum operator, and then we could create these two operators that we now have learned will raise and lower the energies. So we call these ladder operators because they do that. Now, when we got to this point, I had no reason to think that's what these operators would do, right? No reason whatsoever. But people who are far more creative than me came up with these methods. So now we've established that this one here is it always starts that way, is a raising operator, because it raises the energy by h bar omega. And this one here is a lowering operator because it lowers the energy by h bar omega. That's why we have the plus and the minus there for the raising and lowering. And together these are called ladder operators. They're called ladder operators because they take you steps up and down the energy sequence. So with those ladder operators, we were able to rewrite the Hamiltonian in terms of them. We did a commutator with the Hamiltonian and determined that the commutator between A minus and A plus is just 1. And then we went through and said, it can be shown that if the Hamiltonian, the wave function is a function of the Hamiltonian, which is just a way of saying if you found your solutions to the Schrodinger equation, right? That's what the first line says. Then the raising operator is also a function of the Hamiltonian, and the lowering operator acting on the wave function is also a function. But they give you different energies. So they're not the same function, they're a different function that's also a function of the operator. And we worked through to find that the difference in the energies, if we use the raising operator, it gave us the energy one step higher was the energy we had plus h bar omega. So the steps between each energy setting are h bar omega. Then comes the next step. What's new? If we have a lowering operator, the lowering operator will lower us in energy state until we get to the ground state, the lowest state possible.
Is that n equals 0?
It's actually n equals 0 in this case. I still haven't responded to anybody on YouTube, including answering the person who said, why does n have to be 1 or greater? Why can't it be negative? So I need to get to that still. So what we're going to do is say, okay, so what happens if we get to the lowest energy state, right, the ground state, and we put the lowering operator on it? Well, it can't give us a legitimate state, right? It must give us 0 then. Either 0 or it could be some other, the textbook says it could be an infinite unnormalized state. But it's going to have to give us an unnormalized state, an unnormalizable state. And so we have either infinite or 0, and then the author says, in this case, it's 0. So we're taking a little bit of a step here just by saying, okay, in this case, it's going to be 0. And so this gives us a differential equation. Because that lowering operator has the momentum and the position operators in it, And so here we've just replaced A minus, the lowering operator, with what it is in terms of operators. And then we substitute for the momentum operator, its value. And now we have a differential equation. Now, when I get to the next slide has all the math I'm going to be doing here. But I'm going to do my math on this function. So I start with, well, we have I times I. We can combine those, right? And I'm going to move the H bar over to this term. So I'll do it in longhand. So there I've written out the differential equation, just combining I times minus I is plus 1. Now I'm going to divide both sides by H bar. So I get my derivative by itself. And then, and of course, I know Aaron has sat with me in class when I'm all, now what do we do with this kind of differential equation? This is the kind you can solve. So what do we do, Aaron?
We move x over to the other side.
We separate variables. That's what you were describing. So we separate variables, so I'm going to multiply both sides by dx to get it out of the denominator position and move it to the other side of the equation. I also need to move psi 0 to the other side, so I have to divide both sides by psi 0. And what I have now is a differential equation that says d psi 0 over psi 0 equals minus m omega over h bar x dx. Now, there's not a one of us who can't do this math. We're doing these without limits. We're just going to integrate both sides independently without limits, doing a it's odd to me to do an integral without limits. Yeah. So what's the integral of d psi over psi? And what's the integral of x dx? And then I have to put a plus constant. Right, it's part of what I never do in life. Well, I want to solve this for psi, so what do you do to get rid of the psi? Yep, just do the exponential function of both sides. And I have psi sub 0 is equal to e to the minus m omega over h bar, over 2h bar, excuse me, x squared.
And then put a constant out.
Yes, I was going to do it longhand just to make sure we didn't get lost, but you're going quick. So the way that we normally would first write this would be like that, and then we recognize that e raised to a plus b is e to the a times e to the b. And then we recognize since c is just a constant, e to the c is also just a constant. And so I just called that constant A0, my normalization constant for the ground state. All right. You good with that? Close enough?
So is that what number 4 is asking us to do?
No, number 4 is starting with this.
Okay. So this is the given.
Yeah, this is the given in number 4. Now, we have a wave function, a solution to the Schrodinger equation. What's the first thing we always did with our solutions to the Schrodinger equation? We normalize them, yes.
Those solutions, though.
Yeah.
What was it you said?
I thought those were just wave functions. I didn't know that those were solutions.
The wave function is the solution to the Schrodinger equation. Okay, so we have to normalize this. Now I'm going to go to the next slide because I ran out of space there anyway. The link is for a sheet with integrals. Just for integral tables that might be useful in these kinds of integrals, like normalization.
Yeah, like when it's the normalization of the fourth state.
Actually, that's not as hard.
Okay.
No, we will.
Okay.
We will. It's not as hard because of tricks.
Okay.
So if we want to normalize this, we're going to take the integral over all space. That's why it's integral from minus infinity to plus infinity of psi star psi. And so now we've just put in psi star and psi. So the A0 is the only thing that could be complex here. So we have a mod squared integral from minus infinity to infinity. Notice it was over 2 and over 2. When we add those together, 1/2 plus 1/2 is 1. So it's just minus m omega, over h bar x squared. And then the reason I had the link to the integral table is, once again, for Gaussian integrals, I think that's the Gaussian integral sheet that I gave you, like for the test. Actually, I didn't give you that for the test. I have them right now. Who cares? So just going to an integral table, I can't do this integral in my head. We have square root of pi h bar over m omega is what that integral gives us. And so now that we have 1 equals a mod squared, a0 mod squared, square root of pi h bar over m omega, then if we want to solve for a mod squared is equal to square root of m omega over pi h bar, square root both sides. When you square root both sides, of course, square root is a fourth root. And so you have a naught equals, I'm going to just put e to the I theta times m omega over pi h bar to the 1/4 power. What does e to the I theta mean?
Imaginary.
Well, it's complex. It has imaginary and real, so it's complex. The magnitude of e to the I theta is always 1. So that factor out front has a magnitude of 1. And it will give me every possible combination of real and imaginary, because you have an infinite number of solutions, frankly. Theta could be any angle. But for simplicity, we always say, well, the normalization constant, any one of those options will work. So it's easiest if we just take theta is equal to 0 and put that in. So it's always something to keep in mind. In that normalization, mathematically, you have a lot of different factors here because you phase. And so we just choose one, and we're going to be fine no matter what we choose. And I could have chosen to put I out front. I could have put, 1 over square root 2 times 1 minus I. It just would have been more of a hassle. So there's our normalization constant. Well, it feels like we've done a lot. I mean, we have done a lot. We're almost completely done, as a matter of fact. We have a wave function. We've normalized it. We have a relationship between the energy levels. What have we not found? We haven't found the ground state energy yet. So we know the differences between the levels, but we don't know what the ground state energy is, so we don't know any of the energy levels yet. So the first thing I'm going to do here is find the ground state energy.
So in the problems when we're like working with ground state energy at the number 1, is that n equals 1 or n equals 0?
It depends on your system.
Okay.
Right, with the particle in the box, n equals 1 was the ground state.
Okay.
Because n equals 0 gave you a null function.
Yeah.
For this here, n equals 0 is the ground state. And, why is it n equals 0? Well, it's because we define 0 as the ground state to start off the problem. Right? When we said it was the lowering operator on size 0. That's where we said 0 is going to be the ground state. Whereas with the particle in the box, the n actually came out of the math, so we didn't have kind of arbitrary decision there. So I'm going to find the energy. So how do I find the energy in a quantum system? Yes, you have the Hamiltonian operator acting on our state is equal to the energy of that state times the state. Now, to make our lives a little bit quicker, I'm going to introduce something here. I don't know if you guys even see well, you probably don't look at the last year's lectures, do you? On YouTube?
I tried, and then it was too different.
One of the recent questions was, and there's only been like 4 comments in the last week and none in the months before that, so it's not like I get lots of them. And one of the comments was somebody advertised something completely unrelated. But one of them was, do you ever talk about Brocket notation? If so, can you point me to the lecture where you discuss Brocket notation? Well, Brocket notation is a way of designating Dirac notation. And I'm going to introduce Dirac notation here. It's going to come later in the textbook. It is introduced in the textbook. But I'm going to introduce it here because it's a convenient way of writing things. So, have you guys ever heard of Dirac notation or Brock and Ketz? Here is the simplest way of writing things. I write it like this, but it's not really correct unless I put this on there. So if I put the X there, this is a bra X. Why is it called bra and ket? I got to write this one in black. They're brackets. So the bra is the front half of the bracket and the ket is the back half of the bracket. And nobody wants to write ket, C-K-E-T, so that's why it's just bra, the blue, and ket, the red. So if you look at this, this is bra X, ket size 0. And that's equal to our wave function with X as its variable. And so conversely, if I put any guess what that might be? I know you don't know for sure, but any guess?
X with size 0 was it?
That's a good guess. It's the complex conjugate and then we have another thing. What does that mean?
Is that sine 1 squared?
Yes. It's actually a shortcut for writing that. And the ket X, bra X is called, I had it in my head just a moment ago, projection operator. It's a way of projecting into a certain space. So with this notation, it makes some of our work easier, especially for instance, well, when we calculate the momentum and position expectation values. It makes the writing of the problem much easier. So that's the Dirac notation or Brocket notation. Why do I bring them up now? Because it's just a little bit easier to write the relationship. Now, of course, I have to switch. I'm going to just put a slide in between, actually. I've run out of space on that slide. Page manipulation, insert. I'll put in an extra one just in case I take a lot of space. So I want to find the energy level, or the energy for the ground state. So I'm going to have H acting on psi 0 equals E0 psi 0. That's how we write our operator eigenstate equals eigenvalue eigenstate relationship in Dirac notation.
No bracket on the left side?
Right, no bracket on this. So we're going to have, when we do the math, we're going to have, as functions of x, which technically has that little bracket x, but I've never seen it written that way. Maybe we're just all lazy, I don't know. So now let's do our work. So our momentum operator is, or our Hamiltonian is minus h bar squared over 2m d second dx squared plus okay, I got to go back. I don't remember. Putting it in terms of plus 1/2 m omega x squared. So all I have to do is this. And of course, it's not completely trivial because I have to take the second derivative of psi 0. So since psi 0 is equal to, and I'm going to write A0 because it's much quicker to write, A0 e to the minus m omega over 2 h bar x squared. Then that means d psi 0 dx is equal to, okay, you keep the A0, and then you take the derivative of the exponential, which means you bring down the derivative of the exponent. So I'm going to bring down minus 2m omega x over 2 h bar. Notice the 2's cancel. And then I have the exponential, or writing this in a shorter fashion, minus m omega x over h bar psi 0. So there's my first derivative. And then to find the second derivative, of course, I just take the derivative of that. So taking the second derivative, I'm going to have to do the product rule. And so I will have minus m omega x over h bar squared for doing the derivative of the second part times the first, minus m omega over h bar, and then all times psi 0. This last one I did it more in my head because it was product rule of the two, and we've already done the derivative of psi. Is that okay, or should I write it on long form? You okay with it, Chad? Okay. I don't want you to leave, say, well, I mean, he did something. I trust he did the derivative. I trust I did the derivative, by the way. So now I'm going to put this into there. So I have minus h bar squared over 2m times, notice I have a square of a negative, so it's going to be positive, m squared omega squared x squared over h bar squared minus h bar squared over 2m, and this one is going to keep the negative, minus m omega over h bar. So those are the first two, and psi 0 at the end, plus 1/2 m omega x squared psi 0 equals E psi 0. So the red stuff is the same as what we had before, and the green is the second derivative with the minus h bar squared over 2m. So now I just need to simplify, and I'll be done. You have a question?
Yeah, how do you, I know the Hamiltonian is equal to 1 over 2m p hat squared plus all in parentheses m omega x hat squared. Mm-hmm. So how did you substitute in 1/2.
Okay. This is the way we usually write it, but in either case, p hat squared over 2m is equal to h bar over I d dx squared over 2m. And that gives us the minus h bar squared over 2m second derivative.
Okay, you just separated out because we divided it into 1 over 2m.
Well, yes. I put the h bar squared over 2m in front of each of those terms.
Right,
yeah. I did that to make the simplification more obvious, so I can cancel just in one term instead of trying to cancel with two terms. So doing that canceling, the h bar squareds here cancel in the first term. And the m on bottom cancels with one of the m's on top. And so the first term is minus m omega squared x squared over 2. Going to the next term, minus times a minus makes a plus, so the next one's a positive. And then my h bar squared will cancel 1 with the h bar on bottom, and my m's cancel. So I have h bar omega over 2. And then putting the red term, where did I make my mistake? I hate it when that happens. Oh, I made my mistake because I didn't copy that right. If we go back to the Schrodinger equation so that we can clarify my mistake there, the Schrodinger equation has omega squared. I had only written omega, and I got to the part where they're supposed to subtract out, and then I see, whoops. So 1/2 m omega squared x squared. All of that times psi 0 is equal to E 0 psi 0. So clearly the stuff in the bracket is E0. And notice these two add to 0. And so I get E0 is 1/2 h bar omega. Now I have all the energy states, because we had already established before we did anything to find what the wave function was, that E sub n is equal to, E sub n plus 1 is equal to E sub n plus h bar omega. That's what we had already established. So now if I just start the beginning, that means E sub 1 is equal to E sub 0 plus h bar omega. And E sub 2 is equal to E sub 1 plus h bar omega, or E sub 0 plus 2 h bar omega. And I think we can all see a pattern right here, and I don't need to write anymore, do I? If I did E sub 7, what would I get? Yeah. So in general, E sub n is equal to E0 plus n h bar omega, and E sub 0 was 1/2 h bar omega. So that means E sub n is equal to n plus 1/2 h bar omega. So there's our entire energy spectrum. Going back to the picture that's on the first slide of this presentation, remember I told you here's the solutions, and you can see the energy levels are going up by the same amount each time. But the ground state energy wasn't 0. Now we see the ground state energy is 1/2 h bar omega, and then the first excited state is 3/2 h bar omega, the next one 5/2 h bar omega, and so on. So to me, this is kind of an exciting point. We have found the energies completely. We have the ground state wave function. All that really remains is what you have to do for problem 4, finding the other wave functions. So I put in an extra page I didn't need. If we look at our Hamiltonian operator, going back to using the ladder operators. We had two ways of writing the Hamiltonian with the ladder operators. And if we take what we now know to be our energy eigenstate, then we can quickly say that when I have, whoops, I'm going to change the color since I did a bad job drawing anyway. This operates on psi n, and it gives me this. Then that means A plus A minus acting on psi sub n, it gives me n. It's the only way that that can be consistent, right? Right? so A dat, yeah, sometimes say A plus A minus psi n must be equal to n psi n. And likewise, if we were to look at this one instead, oh, gotta not miss. At this one instead, we would say that A minus A plus acting on psi n must give me n plus 1 times psi n. So we can see that there is a relationship here between, well, we can see what the eigenstates are of these combined operators. And in fact, we can go back to, we spent a lot of time proving this initially. All we've done here really is recapitulate that the commutator there is 1. And I think I put that in the right order, didn't I? I can't just put falsehood. I have to go back and check and make sure that's the right order. Yes. So we just recapitulated that work we'd already done. But we've now established that these raising lowering operators working together give us n or n plus 1. And that's going to be useful to us because if we want to find, let's say psi sub 4, the fourth eigenfunction, the fourth eigenstate, then we can do that by doing the raising operator 4 times. The only issue is we do need to normalize still. Just because you raised it doesn't mean it stays normalized. Remember when we had our relationship that said that A plus, where was it? Where is it? Oh, I know, it was in the if statement. No? Yeah, it's in the then statement. This right here. If psi sub n is a function of the Hamiltonian, then so is A plus psi sub n. That statement did not say that A plus psi sub n was normalized. It just said it's also a function. It can be multiplied by any arbitrary constant. It's still a fit. So when we are using the raising operator to find a new eigenstate, we also have to renormalize. And fortunately for you, the renormalization is not going to be take the answer you get after you do it 4 times and normalize it. You could do it that way. It works. But it's actually easier to go through the logic as pertained on this in the next slide. I think it's just the next one. So if I want to raise it, this is showing me how to find psi 1. Okay, so you're starting with psi 0. You're going to have to do this first. You're going to have to find psi 1 by saying, well, psi 1 must be equal to A sub 1, my normalization factor for state 1, times the raising operator only once on psi 0. So you're going to have the raising operator. Here's the raising operator once, and then this is psi 0. Well, that means I do have to go through and I have to take a derivative. I use partials here. Remember, if you only have one variable, it doesn't need to be partial, it can be exact. So I have to go through and I have to do that derivative. And, well, we just did the derivative as it turns out. We did the second derivative too. So doing that derivative, I have the, I times I is minus 1. So this is minus, minus, minus. 3 minuses makes a minus, so it stays minus. H bar stays there. And then taking the derivative, I just put the derivative here, plus MWX, or M omega x. So then I take the derivative, so the derivative of this function here it brings down the derivative of the exponent, so it brought down m omega x over h bar. And then this stayed the same as always. So I multiply these, the h bars cancel. Minus and a minus makes a plus. So this is going to be m omega x plus m omega x. That's 2 m omega x, as luck would have it. So I have in parentheses here, that comes out to 2 m omega x. Out front, we had divided by square root of 2 h bar m omega x. So I'm going to show this one step, just so we're clear on that. Are the steps to here perfectly clear now? I mean, understandable, okay. So going from here to here, this is the kind of place where I make mistakes. So I have rewriting the next to bottom line. And then, as I said, the stuff in parentheses is just 2 m omega x. And then I have, I'm just going to put A0. You know, it's shorter, right? Because that's what that was A0. So now the last step here, like I said, the place where I can make a mistake. I'm going to take this 2m omega and put it inside the square root in the numerator position. So when I put 2 inside the square root, it becomes 4. And m becomes m squared, omega becomes omega squared. My writing here makes it look like that was... And then I have out here still the x, a0, e to the minus m omega over h bar x squared. 2h bar, yes. And then now I can cancel. 4 over 2 is 2 on top. 1m will cancel. 1 omega will cancel. And so that's equal to a1 square root of 2m omega over h bar x. I dropped this off. This disappeared. That's a mistake. That should not have disappeared. It should have still had my A0. That's what you said, right? Where'd the A0 go? E to the minus m omega over 2 h bar x squared. So yeah, I should have had the A0 here still. So that's how you go to the first step. Now, is this normalized? No. But it has the right function in terms of x e to the minus m omega over 2 h bar x squared. And then you have to go through the normalization. So that's how you go from the 0 state to the first state. To go from the first state to the second state, what would you do then? Yeah, you just start up here and you put psi 1 here and you do it again. And then you do psi. So you're going through the raising operator 4 times here. And yeah, that's not pleasant, I know. The reason for it is just to make sure, hey, you've got practice, you see how the raising works.
So when you say put in psi 1?
Well, psi n is equal to a sub n, a plus to the nth power psi 0. So in practice, psi 4 is equal to a sub 4, the raising operator to the 4th power psi 0.
So you have the psi 0 always stays the same.
Well, what I do is I do it sequentially usually. That is, I find psi 1, and then from psi 1 I find psi 2. From psi 2 I find psi 3. From psi 3 I find psi 4.
And you do that.
I do.
How?
I just repeat this process, but instead of having psi 0 out here, instead of having this right here, I'm going to have that.
For psi 0.
Well, it's not psi 0 now, it's psi 1.
Right, but I'm just saying if you're using that psi n equation and you're doing it in sequential fashion, then you practically plug in psi n minus 1 to psi 0 for that term.
Yes, but you have to find psi n minus 1 first.
Right. Yeah, I'm just.
And so that's why you build up. You find psi 1 first, then you can find psi 2. Find psi 2, then you can find psi 3.
How is that easier than just taking psi 1 and using that equation with psi 0?
It's the same thing. It's just the sequence of doing it. Now you could, and I haven't even tried doing this, it might be easier. You could take that operator and find what psi plus raised to the fourth power is, right? Because you're going to have p, one term is p to the fourth, and in terms of p to the third x, and different orders. And it seems like it's going to be hard to me, but it might be easier.
No, that was harder, so.
That was the way you tried?
Yeah. So it makes sense that you can just find them sequentially.
This here, I think, is the way I did it is probably only easier because you have clear delineation, step 1, step 2, step 3 along the way. You do know it's very easy to look up and find what the solutions are so you can check to make sure you did it right. In fact, well,
I know how to.
for the harmonic, the quantum harmonic oscillator, you can look up and find the list of, the first 20 functions or whatever. So it's not like it's, you don't know what you're looking for. You can find to make sure, you find psi 1, make sure that's right. Find psi 2, make sure that's right. So you don't do a lot of extra work. Make a mistake and propagate it. Okay, so now this didn't give us the normalization. It gives us the function, but not the normalization constant. So now for the normalization, we are going to look at, and this is, I showed you pages 47, 48 in the textbook is where this is done. We're going to look at the normalization thing, and we first have to note that an operator can move around. Remember I said the order is really important? You can move an operator in your integral, and instead of operating on the second function, which is where we usually have it, you can move it to operate on the first function, but notice what it was. If it was operating on the first function, then it was a dagger, right? You move it to the other function, it goes inside the complex conjugate. So this is a plus complex conjugate acting on F. And with our raising lowering operators, the complex conjugate of A plus is A minus. And so if I want to find the normalization condition, C sub n here is going to be equal to, it's what we get our normalization constant from, right? C sub n mod squared is going to be our normalization constant. Or no, C sub n is going to be our normalization. When I am raising from n to n plus 1. So it's not the full normalization constant in front of the nth state, it's the normalization going from n to n plus 1. And so if I want to find the normalization for my n plus 1 state, what I have here is, and I'm going to use Dirac notation to make this the shortest possible. So I'm going to have actually, yeah. That should be 1, right? A plus psi n is psi n plus 1. Except for I can move this across to make this is equal to but here's why it gets easier than it would have to be otherwise. A minus A plus acting on psi n, well, we know what that is. we had that right here. A minus A plus acting on psi n is n plus 1. And so this is equal to so now I said this is equal to 1. We have the normalization constants to be concerned about. And so this isn't actually a perfectly correct equation because if you look, actually, yeah, if I just erase that equals 1, then I'm correct. And the A plus psi n, it says here, should give me C sub n times psi n plus 1. So this is actually, yeah, I should have been a little more careful. Okay, that's the way it's correct. And so what we find then is, by definition, this has to be 1 and this has to be 1. So, nice. So the factor to go from psi n to psi n plus 1, C sub n, must be square root of n plus 1. So with the raising operator, we're going to do square root of n plus 1 for each step we go up. Result shown here. A plus acting on psi sub n is equal to square root of n plus 1 times psi n plus 1. Now what that allows us to do is to, I've got 2 minutes, to get a simple equation that is now normalized. If you look at this kind of carefully, if you start at n equals 0, you'd have A plus acting on psi 0 is equal to the square root of 0 plus 1 psi 1. And so psi 1 is equal to A plus over the square root of 1 psi 0. I kept the square root of 1 there because if we did the next one, like if we did A plus acting on psi 1 equals square root of 1 plus 1 psi 2, then we have that and if I want to solve for psi 2, I have psi 2 is equal to A plus now squared over the square root of 1 times 2 psi 0. And if I kept going, I find psi 3 is equal to A plus cubed over square root of 1 times 2 times 3 psi 0, and so on. This pattern doesn't become clear until you get to the third one. And you see, wow, in the denominator, I'm just going to have the square root of n factorial. In the numerator, I have a plus to the nth power. And so that gives you what you're actually going to do to solve problem 4. You're doing this equation. You have to do that raising operator 4 times, and then you're just going to divide by the square root of 4 factorial. 4 factorial, 4 times 3 times 2 times 1 is 24. So you're going to do your derivative or your raising operator acting on 4 separate times. And then when you're all done, you can divide by the square root. You get normalized. a lot easier normalization than it would otherwise have been, right? But you still have all of the work of the using the operator 4 times. One last statement here before we go. And this is just a statement. I know I'm a minute over. You can solve the raising and lowering operators to solve for x as a function of the raising and lowering operators, and p is a function of raising and lowering operators. But that allows you to very quickly find the expectation value for x. So this is how we find the expectation value in Dirac notation. When you have a closed bra and ket, there's an implied integral. And so we have the integral because we have the enclosed bra and ket. And if I put those in, this is trivial. It's trivial because what does the raising operator do? It changes the state. But what do we have if we have psi n, then a constant, and then close it with psi n plus 1? We have two different states. What do we get? I'm going to write this out the way you've seen it before. If I have the integral, so I'm going to have Cn out front because that's what we had defined, psi n star psi m dx. That's what this here gives you. What do you get for that integral? By definition. Because the wave, zero. Because the wave functions have to be orthogonal, then that has to be 0. And likewise, we're going to get 0 for this one. Because we're lower, and so we're going to have psi n and psi n minus 1. And so we can see, without doing any actual calculus, that the expectation value for both x and p has to be 0 here because of the raising and lowering operators there. All right, we're out of time.